Welcome everyone. So in the last class we have started our discussion on high power chargers or modular chargers, where we will be having multiple charging options. So in the first configuration we have seen our diode clamped multi-level converter, where we will be clamping the voltage of various nodes in the circuit by using our clamping diodes. So we have also seen the switching combination of this and number of devices required in this circuit. So the main demerit of this circuit is, for one particular voltage we have one particular combination of switching pulses, or the particular switches are to be on to generate a particular voltage. So we do not have any redundant combination to generate an voltage level. So what is the importance of this redundant combination? When we go for actual loading of this converter, suppose we have load resistance or we have some converter which is put in the following stage after this converter. So when it is drawing some current, we will see that the capacitor voltage which are supposed to be charged to VDC by 4 over here, because we have considered an 5 level configuration. So in this case they will be diverging from this requirement of VDC by 4, and ultimately we will not get the desired voltage levels for the given combination. And second issue is, one of the capacitors will be overcharging and others will be undercharging, or they will be discharging towards 0. So the capacitor voltage will have a runaway event. So that was the main limitation of this circuit. So to address this issue, so we have shifted into our second solution, that was our flying capacitor based solution, where in this case we have replaced our clamping diodes by using floating capacitors, or the capacitors whose voltage are not connected to any fixed point. So they are floating in nature. We charge and discharge them equally over a cycle such that their voltage is balanced. So we have started a discussion on the voltage levels and what will be the switching combinations in this circuit. So in this circuit, if you see, the number of flying capacitors which will be required is m minus 1 into m minus 2 by 2, whereas in our previous case the diode requirement was bit higher than this number, and we have m minus 1 bus capacitors which will be connected across the bus. The voltage rating of each of the capacitors is considered to be VDC by 4 in this case. So that's why if you see, we have one capacitor, two capacitors as CF2 and 3 capacitors as CF1, because they will be charged to 3 VDC by 4. We have seen this combination, switching combination plus VDC by 2. Here we do not have any redundant combination for this plus VDC by 2. That is, one particular combination will give us the VDC by 2 voltage. That is, all the 4 upper switches are on. So this 2 points will be connected with each other, that is, the positive bus will be connected to the output terminal, and we will get plus VDC by 2 at the output stage. Then we have seen the combination for plus VDC by 4, where all these 4 combinations which are listed over here can be used to generate plus VDC by 4, and the status of various capacitors are shown over here. So what is the importance of this redundant state? Suppose all this charging and discharging are maintained or marked by considering positive current. When there is negative current, the exact opposite things will be happening over here. Okay, so this table is entirely for positive current. So when the current is positive, when I mark positive, what is the meaning of that? The current is entering the positive terminal of the capacitor, or it is getting charged. When I mark it as negative, it is getting discharged. If I apply particular this combination, second combination, my CF2 will be charging and CF3 will be discharging. They both will be coming in the path, and C stands for here no change, that is, it is not in the conduction path, whether the current is flowing through the other capacitor, that is not flowing through this capacitor CF1. Okay, so in this case, if you see the 4 combinations now based on my instantaneous capacitor voltage, suppose I have observed that my CF3 voltage has gone below its rated value, that is, over here it will be charged to VDC by 4, in particular sample. While going for generating this VDC by 4, I have observed that CF3 voltage is less than VDC by 4. So I will select this combination such that the current is positive and this combination is selected, so CF3 will be charging. So based on whether my voltage is at the desired level or not, and based on the current direction, I can select this redundant combination. Now let us see this 0 voltage. Okay, so for 0 voltage we have 6 different combinations. So any one of these 6 combinations can be used to generate 0 voltage. So here let us consider this combination, where if you see S1 and S2 are off, so S1, S2, 1, 2 will be on, and S3 and S4 are on. So these 4 switches are on, and now what is the status? If you see F2, it is coming in the conduction path and it is getting discharged. So it means the current will be leaving this terminal. So how it will be leaving this terminal? So it will flow through this path, it will leave the terminals and it will flow through the switch. So in this case, if you see what is the voltage being generated, the voltage is being generated is 0, and CF2 as it came in the conduction path, it is getting discharged. Similarly, I can use any other combination based on where the voltage requirement or the instantaneous voltage of CF1, CF2 and CF3. Now let us see this combination minus VDC by 4. In this we again have 4 different combinations similar to our plus VDC by 4. So here in this case, let us see this example where if you see the S1 is on from the top switch and the remaining two S3 and S4 are on, and my CF1 will be seeing an inverse current or it will be charging, that is this is charging. So what will be the path of that one? It will flow through this and through these capacitors. So if I apply KVL, in this case I will observe that the voltage between these two terminals will be equal to minus VDC by 4, and my capacitor is seeing an inverse current, that is it is entering the positive terminal of that CF1 capacitor. So it will be charging. Similarly, for minus VDC by 2, I do not have any redundant combination. Which combination is applied? In this case, if you see, we have turned on all the bottom switches, that is all the switches are on. So this point gets connected to the negative bus and we get minus VDC by 2 at the output. So what are the advantage of this circuit compared to the previous solution? Here we do not have any requirement of clamping diodes. We use few number of semiconductor devices because we have replaced some of our diodes by flying capacitors or capacitors. Okay. Then switching redundancy, we have seen that we have various combination of switchings which will be giving at the same voltage level. So those redundant combination or the extra combinations which are available with us can be used to balance out the capacitor voltage. So we have seen this also. Now here this is perfectly bidirectional, that is if we are using this in the front end, I can control both active and reactive power independently. Modular extension to higher level is possible. Okay, so it can be extended to higher number of levels, but when I see the device count compared to the next solutions which we were seeing, so here again it has a quadratic relation. If you remember the number of capacitors required, it was m minus 1 into m minus 2 by 2. So it has an square term inside it, or the increment in the capacitor count is quadratic in nature with number of levels. So to some extent we can use it 5 level, 7 level. Beyond that, the number of capacitors requirement will be increasing, and when I compare the footprint of this converter compared to the diode clamp, it will have a higher footprint because the capacitors will be bulkier in nature compared to the diodes. And the reliability wise, the capacitors are less reliable compared to your diodes. So the reliability will also be less compared to the diode clamp circuit. But in flying capacitor, we do not require any additional mechanism to balance out the capacitor voltage. I can use the redundant switching combinations appropriately to balance my capacitor voltages. So this is large number of bulky capacitors are required. So it has a higher volume and cost. Capacitor must be precharged correctly. So while our analysis, we have already considered that the capacitor had some voltage or the required voltage at the starting stage itself, but during the initial startup it has to be done by using some pre-charging algorithm. Voltage balancing requires complex control because at every point of sampling we have to sense the capacitor voltages, current direction. Based on the voltage and current directions, we have to decide which combination of switching pulse has to be given for that particular voltage, such that the capacitor voltage can be regulated. So this has to be done online, so it will be having an complexity, or the control complexity is higher in this case. Reliability is subjected to the capacitor life because the capacitors will be prone to failure. So the reliability of capacitor gives the reliability of this circuit. So it will be less reliable compared to the diode clamp circuit. Application wise, they are used in drives. Here we are discussing about our electric vehicles and our chargers. There also we can use our flying capacitors to naturally balance the voltage. In the DC fast chargers, it can be used as the front end converter, and It can be used as the DC to DC converter, high power DC to DC converter. That those things we will be seeing in the next class. So now they can be used in induction motor control with high frequency response. They can be used as static bar compensators. They can be used in aerospace and traction applications. So in this case, what is the advantage of this term ride through? So here we have energy stored inside the capacitor. Suppose there is some fault, so I can have some time, I can run the circuit in the online mode, or I can keep the converter online because of the existing energy inside the converter. That's what is called as a ride through capability. So because of this reason, so it finds application in aerospace and traction. So in our case, we are more interested in our electric vehicle high power chargers. So there we can use this flying capacitor or diode clamp circuits. Then the next alternative is our Cascaded H-Bridge Multilevel Converter. Okay. So in this case, we see the name Cascaded. It means the very series connection of various H-bridge circuits. What is an H-bridge? So this entity or a capacitor with 4 switches connected in the shape of H, we call that as an H-bridge circuit. So this is series connection of H-bridge cells with an independent DC source. If you see, every one of them is having an independent DC source. So each cell has 4 switches and its own DC source. Each H-bridge can produce plus BDC, 0 and minus BDC, where this BDC is the voltage of the one cell. Okay. So here how this will be generating our plus BDC. So if I turn on the S1 and S4, suppose from this upper H-bridge, if I give pulse to S1 and S4, I will see that the voltage between these two terminals, if I see, it will be equal to the battery voltage. Okay, because S1 and S4 are on, so this is the marked direction of current. So I will get an plus VDC by 4 when S1 and S4 are on. Okay. Similarly, when the complementary condition is true, that is I turn on S2 and S3, I will see that I will get an negative voltage. Okay, so minus VDC by 2. So that's how I will generate the negative voltage. For negative voltage, I will turn on S2 and S3. For positive, I will turn on S1 and S4. For 0 voltage, I will turn on either the top 2 switches or the bottom 2 switches, any one of them. So any one of these 2 combinations will be connecting these 2 terminals with each other, or we will have an 0 voltage at the output. So by just giving the gate pulses, I can generate 3 levels for an H-bridge, that is plus or minus VDC and 0 in the bypass condition. When it generates 0, we say that the H-bridge is in the bypass mode. Total output will be equal to sum of individual capacitor output with n cells. We will get an voltage level which will be equal to 2n plus 1. Okay. So in the previous case, if you remember, it was m plus 1 or n plus 1. Whereas in this case, if we have n number of cells, we will get 2n plus 1 voltage levels. Okay. So this is one of the advantage of this circuit. We get higher number of levels for a given number of H bridges. For a given number of H bridge switches, we have 2n plus 1 number of output voltage levels. More is the output voltage levels, more will be the waveform nearer to our sinusoidal, or THD will be less. In this case, we are not considering all the redundant combinations. We have shown a particular combination. If you see, I am generating positive voltage. In the first case, I am generating positive voltage from all the 4 cells. What is the meaning of that? All the cells have S1 and S4 in the inserted condition. So I will get 4 VDC at the output stage. Similarly, in this case, when we go for the maximum positive or maximum negative voltage, we will not find any redundant combination. That will be true over here also. We will not have any redundant combination for generating 4 VDC. Whereas for other cases, we will have redundant combinations. Let us see over here. So in this case, I am generating 3 VDC. So I have inserted the first cell in the positive voltage mode. So what is the meaning of that? I have turned on S1 and S4. Similarly, second for S1 and S4, and third case S1 and S4. And in the last cell, I have bypass rate, suppose by turning on S1 and S2. Okay. So here, as we are considering 4 H bridges, so it will be generating 9 number of levels at the output stage. Okay. So in this second combination, so where is the redundancy? Here if you see, we have marked only one set of combination which will be giving us 3 BDC, but now how the redundant combination can be generated over here. So if you see, I have turned on 3 submodules to generate, or 3 H bridges to generate positive voltage, and I have kept one in the bypass mode. This one can be first cell, second cell, or the fourth cell. Okay, so here we have considered the fourth cell to be in the bypass mode. Similarly, we can have one more combination where 1, 2 and 4 will be inserted, or 1, 2 and 4 will be generating positive voltage and 3 will be in the bypass mode, and so on. So we will get 4 different combinations to generate 3 VDC by 2. So I can again use these redundant combinations to balance out the voltages if we have capacitors instead of DC sources over here. Okay. Now this next combination 2 VDC, again here I am using 2 cells to generate positive voltage, 2 of them are in the bypass mode. So it will again give me 4 different combinations. Similarly, what can be the other combinations? Instead of bypassing these two, I can insert one in the positive direction and one in the negative direction. So they will be cancelling out each other. In that way, I will get further more combinations. So I can use any of these combinations to generate 2 VDC by 2 VDC voltage. Okay. So 2 VDC voltage, we have plenty more number of combinations. Similarly, when I see this VDC, again we will have plenty number of combinations, that is positive by one cell, or that one cell can be any cell from 1 to 4. The other combination is I can insert one in the positive and one in the negative, so that they will cancel out and we will be left with net one positive. So in this way we get plenty number of combinations to generate VDC. Okay. So as the voltage level decreases, the number of combinations possible increases. Okay. Similarly, for 0, I can insert 2 in the positive and 2 in the negative direction, still I will get the 0 voltage. Similarly, I can have 1 plus 1 minus 2 in the bypass combination. All these states will be giving me 0 voltage. So I have redundant combination in cascaded H-bridge topology also. Similarly, on the negative side, again this is the bypass condition. I have turned on the fourth bridge where S2 and S3 are turned on. So that will be generating a negative voltage. Similarly, this fourth switch can be shifted to or exchanged with our first, second or third, where they will be generating negative voltage. Remaining cells can be in the bypass mode. I can have plus and minus to cancel out the voltage, so that I will be left with one net negative voltage. So on, we will have many combinations for minus VDC. Similarly, when we reach at minus 4 VDC, there we will observe that all the 4 H bridges will be inserted to generate negative voltage and will not have any redundant combination for this voltage level. Okay. So when I generate peak positive or peak negative, I do not have any redundant combinations, whereas for other voltage levels, I have redundant combinations similar to my flying capacitor configuration. Now what are the merits and demerits of this circuit? So it is perfectly modular compared to the previous cases. There we do not have this modular flexibility. So what is their modular flexibility? If you see, we have one small subset or a building block of the circuit. I am just repeating this number of H bridges to generate an n plus 2 n plus 1 number of level circuit. So as we have an subset or an modular or an sub building block of the circuit which can be used repeatedly to construct the entire circuit, I say when I have such type of flexibility, I say that converter is modular. So what is the importance of this modularity? So when we go for maintenance of this circuit, when the circuit is modular, or in future suppose I have developed an 11 level converter, now I want to shift it to 13 level, so I can just add one more module and go to the 13th level. Whereas in the previous cases, whether it was diode clamped or your flying capacitor base, they do not have this modular flexibility, so easily extendable by adding more and more H bridges. Now no clumping diodes or no flying capacitors in this circuit. Equal voltage stress across all the switches. What will be the rating of the switch over here? They will be equal to this single cell voltage, that is in our case it will be equal to VDC. Switch 1 to 4, they will be rated to VDC voltage. So why VDC? If you see, when the switch 1 is on, So this will be connected to this bus. So what will be the voltage across S3? It will be equal to the DC bus voltage, that is VDC. So the switches are equally rated, or the ratings of S1 to S4 will be the same. It will be equal to the DC link voltage. Now, if we have suppose fault in some one of the cell, I can easily bypass it and still continue the operations with, suppose I do not have any extra cells available with me. So I can just reduce the number of levels. It will be reducing from 2n plus 1 to 2n minus 1. Okay, so two number of levels will be reducing if I have one fault in one H-bridge. But still I can continue the operation of the circuit till I get scheduled outage of this circuit. Now, needed for demerits. So every circuit will have its own merits and demerits. So what will be the demerits of this one? It requires separate DC source. I cannot have an combined DC link over here, or I cannot connect all the cells to an high voltage DC. So we do not have an independent DC link over here. Every cell will be having its own DC source. So this was one of the major limitations in our Cascaded H-bridge. So it was not used for high voltage systems where we wanted a common DC link, but it has gained interest in our electric vehicle applications because each of these ports can be used as one charging ports, or it was used in our PV where each H-bridge can be connected to an PV panel by using a DC to DC converter to regulate the voltage. So for this type of applications and for STATCOM where we do not require any DC link, for those applications this Cascaded H-bridge was very popular. Now they are being used in our electric vehicle applications. We will see some examples of this application of this Cascaded H-bridge in the next class. So here for grid connection applications, it requires multi-winding transformer or many DC supplies. Okay, so that's why it was not being used popularly in the olden times, but now after the electric vehicle has gained its importance, this circuit has been used in this electric vehicle applications. More complex control as the number of levels increases, because I have to maintain the individual DC link voltages. If suppose they are from PV or some other thing, we have to maintain the voltage. So the control becomes more and more complex because we have redundant combination based on the online parameters. We have to select one particular switching combination. Higher overall loss because of multiple isolated supply. So we will be having higher cost of this converter because it requires independent DC supplies. Applications for BESS, PV storage, where we can have independent DC link voltages. This was quite popular in PVs and our battery energy storage system. So it is an application where we will have battery bank to support the grid, where we have high amount of renewable energies. When they are not available or the renewable energy power is decreasing than the desired value, we can use the energy stored inside the battery bank. Then medium voltage drives, it was very popular for our STATCOM applications because it had flexibility of replacing this DC source by capacitors, because in STATCOM it is meant for only reactive power where the active power consumption is 0, so it does not require any DC link. So for those facts or your starting compensator application or STATCOM applications, this Cascaded H-bridge was very popular. Then HVDC and our reactive power compensation. In HVDC where we wanted this reactive power compensation, there it can be used. After this we have seen three types of multi-level converters. So each one of them had their own merits and limitations. All of them have a common limitation, that is they require quadratic increment in the device count when I increase the number of levels. So in 2006 there was a thought process, can I eliminate this quadratic increment in the device count while increasing the number of levels? So as a solution to that, we have got this multi-level converter configuration, where it is called as modular. As we have already discussed, it will be highly modular. It means it will have a small building blocks. It will be repeatedly connected as per the requirement of the rating on the number of voltage levels at the output stage. So more is the voltage level, more will be the number of cells which will be used in this circuit. So in this MMC, what is the typical terms used? So if you see, it has two arms, upper arm and lower arm per phase. Midpoint of that is the AC output terminals. We have DC link connected at the top and bottom. We have two arm inductors, and this entire two upper and lower arms are cut together called as one leg of the circuit. In MMC, we have, for each phase we have one leg which is connected across the DC link. Each leg consists of two arms, upper arm and lower arm. Midpoint of the two arms contains the AC output terminal. Now let us see the working of this. Before that, we will see the basic building block, that is our submodule or cell. Sometimes it is called as cell or an submodule. Submodule is the component which is the building block of the circuit. I can just repeat n number of submodules to construct an n plus 1 number of MMC. Okay. So here in this submodule, if you see, we have an capacitor and two switches S1 and S2. It may be IGBT or MOSFET based on the power rating for which this circuit has been designed. If my S1 is on, I will get an finite output voltage which will be the voltage of this capacitor. When S2 is on, I will see that the voltage generated by this submodule will be 0. I say that the submodule is in the bypass condition. So by using each of the submodule, I can generate two voltages, that is either the capacitor will be inserted or it will be in the bypass state where I will get 0 voltage. This submodule where we get positive or 0 voltage, it is called as your unipolar submodule. We have various types of unipolar submodule. This is the simplest one of that is called as half bridge submodule. The next is our full bridge submodule, where we have two legs and one capacitor at the DC source. So here in this case, if you see, we have S1, S2, S3, S4. It is similar to that of our Cascaded H-Bridge, but here we are using that as an submodule in the circuit, and it is not having an independent DC source as per our previous circuit. That is, in the Cascaded H-Bridge we required independent DC source, whereas in this case it is just a capacitor whose voltage will be balanced by using the switching combinations. So what can be the voltage it can generate? Similar to our Cascaded H-Bridge, this full bridge also can generate three voltage levels. That is, when S1 and S4 are on, it can be inserted in the positive direction. When S2 and S3 are on, it will be generating a negative voltage. When S1 or S3 or S2 or S4 are on, it will generate 0 voltage. So by using one full bridge submodule, I can generate three voltage levels, whereas by using an half bridge submodule, I can generate one positive voltage and 0 voltage. Okay, so positive and 0 are possible with the half bridge, and positive, negative and 0 are possible with the full bridge. So this negative voltage will be very useful when we go for DC fault operations. So now let us see what happens if I connect two half bridge submodules in series. This independently can generate and positive and 0 voltage. This also can generate and positive 0 voltage. Now if I use these two submodules with a time shift as shown over here, I will see that I will be generating an stepped waveform. Okay. So I have just used two half bridge submodules in series and I have generated an stepped waveform. Okay. Similarly, if I increase the number of submodules which are in series, I can generate an stepped voltage which can be varying from 0 to an higher voltage. Okay. So what is the meaning of these steps? If you see, I can have a sine wave over here. If I go to Fourier series expansion of this circuit, we will see that it will have a sine wave. Okay. So more is the number of steps, more will be the waveform moving towards the sinusoidal output voltage. Now this is this series combination of a cell, we call that as an arm. It may be upper arm or lower arm. Now till now what we have done, we have understood the working of single bridge, then we have gone to the output of two half bridges, then we have seen many half bridges in series to construct an arm. Now we have connected both the arms, that is an upper arm and lower arm, which is containing n number of half bridge submodules in each of them. Okay. So now what happens when we have two arms connected in series? Okay. So now output voltage, that is the voltage which is generated across this terminal A or the AC terminal, it will be the difference of the voltage which is generated by the upper arm and the lower arm. Let us see as an example. So here if you see, this is the upper arm voltage, this is the lower arm voltage, whereas the output voltage is the average of this one. So we will see one by one. So now here we are considering an 5 level MMC, that is MMC generate n plus 1 number of levels similar to our flying capacitor and diode clump circuit, where n is the number of hybrid submodules connected in an arm. Okay. So here we have 5 levels because n equal to 4 in this case, we have 4 submodules in one arm. So it will generate 5 number of different levels. If you see what are those 5 levels, minus plus and minus VDC by 2, plus and minus VDC by 4 and 0. Okay. So these are the discrete 5 different levels which can be generated by using this MMC circuit. Okay. So here in this first switching combinations, where we have inserted all the 4 submodules in the upper arm and we have bypassed all of them in the lower arm. Okay. And now here we have an VDC voltage over here. Okay. So what will be the voltage of each of the submodules? In this case, if I apply KVL in the outer loop, now I see that only 4 cells are there in series and they are connected in parallel with VDC. Okay, or these 4 cells has to block this VDC voltage, so each of them will be rated to VDC by 4. Okay, now if I apply KVL, so generally we split this voltage, so where the IC output voltage will be generated, this will be VDC by 2, this will be VDC by 2, and midpoint we consider that as the reference point or the neutral point, that is the load will be connected between these 2 points. So now in this case what will be the output voltage? So now let us see, this circuit has 3 loops, one outer loop which we have just now used to find out the voltage of each of the submodules. Now we have upper loop as well as lower loop. Okay, so for successful switching combination or any valid switching combinations, the KVL in all the 3 loops has to be satisfied, or else we will have a huge amount of current in the circuit and that particular combination is not a valid combination, or we have made some error while calculating the submodule starter, that is whether it will be inserted or bypassed. Okay, so in this case if you see, when I apply KVL in the upper path, I will see if I travel in this way, minus VDC by 2, minus VDC by 2, then plus of 4 into VDC by 4 plus VA is equal to 0. When I calculate VA, now it will be equal to minus VDC by 2, which is shown over here. Okay, so this particular combination, if you see the red line, so that's what is the current state which we have got by using this combination, that is 4 cells on the upper arm are inserted and 4 the lower arm are in the bypass condition. Okay, and what is the voltage generated by the upper arm? It is equal to VDC because all 4 of them are on and each of them is rated to VDC by 4. VDC by 4 into 4, that will be generating VDC. What is the voltage generated by the lower arm? It is equal to 0. Now let us see the KVL or apply KVL in the lower loop. Okay, so if I apply KVL, I will see minus VDC plus minus VA plus 0 because the entire lower arm is in the bypass mode, equal to 0. So again VA will be equal to minus VDC by 2. Okay, minus VDC by 2, KVL of the lower loop, minus VA minus 0 equal to 0. So my VA will be equal to minus VDC by 2. Okay, whether I apply KVL in the upper loop or in the lower loop, this is for the upper arm, this is for lower arm, or in the lower loop. So if I apply the KVL in the upper loop or the lower loop, I will see that in both the cases it will be generating VDC by 2, and in an entire arm if I see, it is generating VDC. Okay, so if I consider the loop 3, that is the entire bigger loop. Okay, loop 3. So in this loop 3, it is generating, or an leg of MMC is generating VDC. Okay, now let us see the next combination where we have used 3 cells from the upper arm and 1 from the lower arm. Okay, so in this case what will the voltage? So if I apply KVL in the outer loop. Suppose in the outer loop, if you see, again VDC will be equal to the sum of 4 submodules which are in the inserted condition, 3 from the upper arm and 1 from the lower arm. Again it has 4 cells with each rated to VDC by 4. So the outer KVL is satisfied, that is we have 4 cells with of rating VDC by 4 in the path, so it will be generating VDC. So KVL is satisfied in our outer loop. Now let us see the inner loops. In this case, minus VDC by 2 plus 3 into VDC by 4 plus VA is equal to 0. Now VA will be equal to minus VDC by 4. Okay, that's what is marked over here. Okay. Similarly, in the lower loop, if I apply KVL in this case, minus VDC by 2 minus VA plus VDC by 4 is equal to 0. Again VA of the output voltage is equal to minus VDC by 4. That is in the upper arm, or when I go in the lower arm, I will see that it is generating a voltage which is equal to minus VDC by 4. Okay. So in this case, where is the redundancy? If you see, we have turned on the top 3 submodules, but I can turn on any 3 submodule out of the 4 from the upper arm to generate this minus VDC by 4. Okay. Similarly, we have various combinations in the lower arm also. Here we have selected one submodule to be generating the voltage. It can be any one out of the 4. So it is again dependent on the instantaneous capacitor voltage and the direction of current. If the direction of current in such a way that it is charging, I will select the submodule which has the least voltage, such that it will be inserted and get charged. Similarly, for the 0 voltage, 2 submodules should be inserted. Again we can apply the KVL in the all the 3 loops, upper loop, lower loop and the outer loop. In this case also we will see that the voltage is 0 at the low terminals. In this loop, minus VDC by 2 plus 2 into VDC by 4 minus VDC by 2 plus VA is equal to 0. So again VA will be equal to 0. Okay. Similarly, in the lower loop also I will see that it will be generating 0 voltage, and in the entire leg, if you see, again we have 4 submodules in the inserted condition, that will be equal to VDC by 4 into 4, so equal to VDC. So outer loop is also satisfied. So till now what we have seen, we have gone through the various switching combination of an MMC. We have seen how the voltage levels are generated. We have seen the discussion on the multi-level converters, all the 3 types of them, their merits and demerits. And now we are discussing about our MMC. Then we will see how it can be used in our charging applications in the next class. We will continue from this point in the next class. Thank you.